Welcome to This Explainer. I'm speaking to you today not just as a host, but as a climate scientist, delivering what is, quite frankly, an urgent briefing on Europe's future water security. We're looking at a profound, literal transformation of our planetary life support systems. It goes way beyond those simplified headlines you might have seen about a cooling continent. Today, we're going to dig into the hard data and the latest Earth system models to understand exactly how shifting ocean currents are threatening the very foundation of Europe's hydroclimate. Let's get right into it.
So here is the big question guiding our entire analysis today. What actually happens to Europe's water supply if the ocean's heart stops beating? The stakes here are just extraordinarily severe. Consider this. Roughly 80% of European agricultural land is rain-fed. That means it relies entirely on consistent, predictable, seasonal rainfall. We aren't just talking about a few dry summers or having to water your lawn a little less often. No, we are looking at the potential for a complete structural reorganization of seasonal rainfall, evaporation rates, and overall agricultural viability across an entire continent.
Okay, let's dive into this by defining exactly what we are dealing with here. The AMOC, or the Atlantic Meridional Overturning Circulation, is this massive sister of ocean currents. You can kind of think of it like a giant global conveyor belt. It transports warm, salty water from the tropics, including the Gulf Stream, which you've probably heard of, all the way up into the North Atlantic. Once it gets there, the water cools down, gets denser, and actually sinks before flowing all the way back south. Now, this incredible system carries roughly 1.5 petawatts of heat northward. To put that massive, kind of abstract number into perspective, that is the energy equivalent of millions of nuclear power plants operating simultaneously, just constantly pumping heat into the North Atlantic. That massive transfer of energy is the primary reason Europe enjoys the relatively mild, stable climate it has today. It's basically Europe's ultimate climate regulator.
Section 1. The tipping point approaches.
So our models are indicating that this absolutely crucial climate regulator is in deep, deep trouble. And honestly, we're rapidly moving out of the realm of theoretical physics and into observable reality. The AMOC is showing some really alarming signs of instability. You see, as global temperatures rise, melting ice from Greenland and increased atmospheric rainfall are basically dumping vast amounts of fresh water directly into the North Atlantic. And this fresh water, it lowers the ocean's density, which actively chokes off that crucial sinking mechanism that drives the whole circulation. Because of these shifts, the data we're looking at is just striking. Recent peer-reviewed science, which is based on some rigorous reanalysis of observational data and salinity metrics, estimates a 59% probability of an AMOC collapse before the year 2050. I really want to let that sink in for a second. 59%. And that estimated collapse time falls within a confidence interval of 2037 to 2064. So this isn't some science fiction scenario for the year 2200, right? This is a modeled statistical probability happening within our lifetimes, driven by these self-amplifying feedback loops.
And this brilliantly illustrates the dramatic surface temperature changes that these models project when that system starts to wind down. If we see a large AMOC decline, the Northern Hemisphere is going to experience a massive drop in temperatures. We're talking about a cooling effect so severe that it could completely offset the greenhouse gas warming we've been predicting for the UK and Europe. But here is the absolutely crucial piece you have to understand. Planetary cooling from a collapsed ocean current doesn't just lower the global thermostat. It literally rewires the entire atmosphere.
Section 2. A shift to extreme drought. So what does this planetary cooling actually mean for European rainfall? Well, when the Northern Hemisphere cools relative to the Southern Hemisphere, the thermal equator, which is that belt of the highest temperatures around the Earth, shifts south. This thermal equator dictates our weather. So as it shifts, it forcefully pulls the tropical rain bands right along with it, pulling them completely away from Europe and reorganizing atmospheric circulation and storm tracks. For Europe, this translates to an intense, devastating reduction in available water. To measure this, we climate scientists use a metric called the Climatological Potential Precipitation Deficit, or PPD. Simply put, PPD looks at the balance between the water falling from the sky as rain and the water evaporating from the ground back into the air. And the latest runs from the Community Earth System model point to severe shifts in this PPD. We are looking at a massive transition toward longer, much more intense dry seasons across almost the entire European continent. The rain is simply going to stop falling the way it used to.
And look, the severity of this drought shift really cannot be overstated. Professor Stefan Rahmstorf, who is the co-head of Earth System Analysis at the Potsdam Institute for Climate Impact Research, explicitly warned that an AMOC collapse would bring devastating consequences for weather patterns, ecosystems, and food security.
It's such a major reorganization of the global climate system that the impacts are universally recognized by experts as being absolutely catastrophic for our current agricultural systems. This isn't just an abstract data point on a chart. It is a fundamental threat to the availability and the cost of the food on our tables, and the water flowing right out of our taps. Which brings us to Section 3, Comparing Climate Scenarios. So just how bad does it get? To figure that out, we have to look at how these scenarios compound on top of each other. Because remember, the impacts of an AMOC collapse aren't happening in a vacuum. They're happening on a planet that we are actively warming. We need to explore how the specific drought outcomes change under different human-driven emission pathways. In climate science, we use these scenarios called representative concentration pathways. Essentially, we compare a pre-industrial baseline to modern projections, like RCP 4.5, which is a moderate emission feature, and RCP 8.5, which is basically our high-emission worst-case trajectory. When we contrast that baseline pre-industrial data with these higher emission scenarios, we see anthropogenic warming acting as a massive threat multiplier. Think about it. If the AMO collapses in a pre-industrial climate, the resulting drought is driven almost entirely by reduced precipitation. The rain fails, and yes, that's bad enough. But if the AMO collapses in a high-emission future, you don't just lose the rain. The higher background global temperatures drive extreme potential evapotranspiration. Basically, the hotter air acts like a giant sponge, just aggressively sucking whatever moisture is left right out of the soil. Now, what's really interesting about this slide is how intensely these numbers compound under anthropogenic warming. The data reveals a really stark contrast. Under a collapsed AMOC in a moderate emission scenario, that's the RCP 4.5, the dry season intensity in Sweden jumps by 72%, and in Spain by 60%. But if we push to a high-emission scenario, RCP 8.5, and combine that with an AMOC collapse, that drought intensity increases by over 100%. It literally more than doubles. A collapsed AMOC combined with higher greenhouse gas emissions essentially locks Europe into this devastating double bind of zero rain and extreme evaporation. Section 4. Impacts on food and water. Moving down from these big atmospheric models directly to the ground level, we really have to look at the tangible threats to human life and the societies we've built. The cascading agricultural effects here are profound. We're looking at a severe water deficit happening precisely when we need that water the most, the absolutely crucial April to September growing season. Models project a sharp decrease in agricultural land production right from spring into summer. The United Kingdom faces intense vulnerability when it comes to its crop yields. Across southern Europe, soil moisture is just going to plunge as the ground completely bakes, and we see drastic increases in what scientists call SPI6 severe drought extremes. So SPI6 stands for the Standardized Precipitation Evapotranspiration Index over a 6-month period. Essentially, this index is just measuring the cumulative compounding effect of intense heat mixed with a total lack of rain over an entire growing season. Under these conditions, the probability of these back-to-back devastating agricultural droughts just skyrockets, which would render our current farming practices in many of these regions completely unviable. Section 5. The window for action. This grim, localized data has totally mobilized the scientific community. Recognizing the sheer scale of this threat, over 40 leading AMOC experts recently penned an open letter to the Nordic Council of Ministers. Their message was a unified, urgent plea. They stressed that because Nordic and European countries are sitting right in the crosshairs of these immediate hydroclimate shifts, leaders absolutely must use their diplomatic power to push the world for rapid, ambitious emissions reductions. Keeping global warming within that 1.5 degrees Celsius limit of the Paris Agreement, that is our best defense against triggering this tipping point. The science is incredibly clear here, folks. The ocean currents that built the European climate are destabilizing, and anthropogenic warming is acting as a brutal multiplier on the ensuing droughts. So I'm going to leave you with this final thought. The data has given us an unprecedented look into a remarkably dry future. Will we heed the warnings of our water and change course, or will we simply wait until the well runs dry? Thank you so much for joining me for this explainer. Keep questioning, keep learning, and whatever you do, don't look away from the data.